wait a few minutes. We've already started recording. More questions on the project?
Not really.
But everything makes sense, right? There's nothing strange.
For part E of question 1, where you're plotting, you're changing the time step size,
right?
And you're seeing how it's affecting the error. I was expecting a straight line, but I'm getting a curve. Is that normal?
I have to check, but it's going down, I hope. The error decreases with R. Okay, so we can start. Yeah, if you have questions about the project.
Are we supposed to make the animations in parallel view only?
For the homeworks and projects, the question is, are we supposed to use parallel view strictly? No, you can use whatever you want. Parallel view is a very nice tool. Not useful for 1D project. It's very nice for 2D, especially for 3D. Any other questions? I will try to find something that converts MATLAB data to parallel view for you, in case you want to use it. But you don't have to. No? Okay, so last time we were talking about time integrators. So today we'll finish that story. And then I will show you some very simple coding tricks. Okay? So I will actually code it up and we will see how it affects the performance of our code. Okay? And they're very, very simple things. And it's related to how the hardware is arranged, how the memory is laid out. So when I started writing code, I never thought about these things. But as you get more experience, you realize swapping 4 indices, the for index X, for index Y, just swapping those two can make a huge difference. Now I'll show you today how. Okay, so before we get to fun stuff, let us finish off with the time integration. So, and we were working with a very simple example, a toy example, right? But in reality, what happens is we have these data points. Okay, and we're at these data points, we might know the x coordinates. Let's say x equal, this is 0, 1, 2, blah, blah, blah. And we might be given the derivative, right? Del x by del t is, let me get the numbers right. Okay, I remember it was 5, 3, and 1. 5, 3, and 1. Yeah, perfect. 5, 3, and 1. So this is in meters, this is in meters per second. Okay, so in a numerical problem, we have something like this. We know the coordinates, we know the derivative. And physically, what this can represent is it can be, okay, we have this straight sort of channel, and we know that water flows at these given velocities at each of these points. If I drop a bead at the origin, point 0, and what is the question that comes to your mind? What's the first thing? If I drop a bead over here, what do you want to know?
What is the x in the next times?
Yeah, how the bead will move through the fluid, right? Which is, what is its position at some time? Here, there's no time. There's just, at these x locations, we have the velocity. So we basically want the trajectory of this passive scalar, which will not change the fluid velocity. Okay, and so at t equals 0, we initialize a particle at x equals 0. What is x end at t equal 2? And again, we are sticking to very simple examples, but it all builds up to the advection equation, which is what we were initially after. All right, so tell me, what is the simplest thing we can do?
Linear changes.
Yeah, linear change. So that's what we started with. X star plus u star times delta t, which is 0 plus 5 times 2, which is 10 meters. Okay? So, and we know the analytical answer for this, again, from the example we were working through last time, is 6 meters. Equal to. So the error is roughly 40%. Okay. So this is a quick approximation, but it's a very crude approximation. And we talked about the midpoint method and how that makes things better. So there we would say, so midpoint would be x end equal x start plus u at time equal 1 second times delta t, right? Which in this case is x start is again 0, u at time equal 1 second, I gave you is 3 times 2, which is 6 meters. So this is exact. It matches the exact answer. All right, and this happens because we got lucky. The data I gave you is parabolic, so this works. But the very nice technique that you can use for this sort of integration is called Runge-Kutta. And it comes in several orders of accuracy. There's Runge-Kutta 2, Runge-Kutta 4, and higher orders. 2 and 4 are the most used ones. So what's the formulation of this? So here, it's basically, say K1 is f of xn, tn. Then what happens next is, so this is my derivatives path, where f is del x by del t, right? So this is my known derivative at the current time. And then, so this is step 1. Step 2 is take a half step. And evaluate the derivative again. All right, so we just say K2 is again f of xn plus, we take a half step, so that would be delta t over 2 times K1. K1 is the time derivative, so that would just be the velocity in this case. But it doesn't have to be the velocity. These are very general things. Variables can be whatever you need them to be. En plus delta t over 2. Okay. And then the final thing is go back to xn and take a full step, but with slope k1, slope k2. Okay, so what that means is my new xn plus 1, which is what I'm after, is just xn plus K2 delta T. Okay. Again, K's are the derivatives, which in our particle tracking case is just the velocity. So that's what this means. Does this make sense? Okay, so let's see how we can apply it to this, the one-dimensional channel that I made up, right? Okay, so let's see. Okay, let's apply RK2 to the 1D case. All right, so I will need your help here. Let me redraw the channel. So this is 1, 2, 3, 0, 1, 2, 5, 3, and 1. Okay, so let's do the first step. Okay, so then step 1. K1 equal what?
We're starting at 0.
Yeah, let's start at 0. So
It's 5.
xn equals 0. All right. So K1 is 5, right? It's just del x by del t at x equals 0, t equals 0, which is 5. Okay, this is known. Okay, next step is K2 equal what? So basically, what does K2 represent in our channel case?
Halfway between step 0 and 1 on the velocity.
Between 0 and 1. So you're saying
Between step 0 and 1, so 5 and 3.
Perfect. Yeah. So between step n and step n plus 2, what is the velocity? And we said we will estimate this using, this is our estimate for that, right? We will take half a step in space from the starting point and then re-evaluate the velocity there. So the first thing we need to do is take half a step, right? So we need to find xn plus half is xn plus delta t over 2 k1, right? I'm just copying this down, what's written in here. And this is 0 plus a, we said we need to go 2 seconds, right? So it's 2 over 2 times 5. K1 is 5 in here. Okay, so this is 5 meters. All right, let's go back to our given data that we know and figure out did I do something wrong? Wait. Oh yeah, wait a minute. This is sorry. This is not x. This is time. This is 1 second. Right? This is second, and the x should actually be.
So that's n, right?
All right, I've done something wrong. Just give me 1 second, and I will figure it out. Xn plus r is 5 meters. Okay, fine. Okay, it's not wrong. Okay, I had something else in my head, but that's fine. So we need to know what the velocity at 5 meters is. And I only gave you 3 data points, so let's make this more. And let's make this 0 meters, 1 meters, 2 meters, 3 meters, 4 meters, and 5 meters. okay? And we can say this is -1, let's see, 2, 2, -3, 2, -5. Okay. Yeah, so this is not exactly the parabola that we solved last time, but that's fine. It's just another numerical example. Okay, so at all these x points, we know the velocities, and we've taken half a step in time, and we've gone 5 meters, right? So K2 is what? Can we bring back the formula? So K2 is the derivative at this half step, okay? So from our data, what should K2 equal?
4.
4, you're saying 4 because, why 4?
Between 0 and 1.
Is it 5, -5?
It's -5.
Yes, it's -5, yeah. Okay. That's weird. Yeah, I wish I had not picked X, but yeah, that's fine. The integration doesn't care about physics, so the procedure is fine. Okay, so we took a half step. So where are we after 1 second? We are at 5 meters. Now, what is K2? K2 is the derivative at this half step, which is -5. Okay. Then the next step in Runga-Kutta is you take this K2 and this is your full step derivative. So we will say a full step will just be equal to my starting step plus delta t times K2. Okay, which in this case we found it to be 2 times -5. Minus 10. So that's how, if you're doing.
Just a doubt.
Once more.
Just a doubt. Isn't this supposed to lead to an implicit equation? Because according to the Runge-Kutta equation, K2 is supposed to be calculated at delta t by 2 and not at t equal to 0.
Yeah, so your point is very correct, which is, so what the comment is K2 should actually be evaluated at this half step in space, but also step forward in time, right? So for real data, your velocity might also be changing in time. But here, the data I gave you says at these spatial points, the velocity is fixed to be this, no matter if you look at it at 1 second, 3 seconds, right? So it's just, it can be water flowing at these very fixed velocities. Okay? So in this case, our K2 at xn plus half and t plus half comes out to be -5. Does that make sense? Yeah? All right, perfect. So yeah, that's another difficulty, you know? When you're doing this in reality and your u is also evolving in time, then there's a difficulty in you have to solve for the new u at this half step, as well as affect your scalar. Okay, so there's the imagine the computation increases immensely, even for this two-step process. Now there's another popular RK4. It's a 4-step process. So you have to take 4 intermediate steps, not just 2. Okay, so it's expensive, but it comes out to be very accurate. And compared to implicit methods, the cost is negligible. Well, not negligible, but it's significantly lower than implicit methods. Okay, so would you use RK2 over RK4? Well, let me explain what RK4 is first. So everything here in the RK2 case makes sense? Yeah, physically I didn't pick a very nice example, but well, the procedure is this. So let me show you RK4. So you don't need to rewrite this RK2 versus RK4. I will just rewrite the RK2. We said K1 equal and f of xn tn. K2 is f of xn plus delta t over 2 K1 tn plus delta t over 2. And xn plus 1 equal xn plus delta t K2. Alright? So you will, RK4 does something very similar. Let me see if I have enough space. RK4, again, K1 equal F. And let me make sure I don't mess up my coefficients. Okay, K2 is the same. Now, there's a K3, okay? And K3 is, you again take a half step starting from xn, but this time you use this new slope that you've computed. So it's xn plus half step K2, comma, tn plus delta t over 2. And then there's a K4, which says, all right, now you take a full step using this K3. All right, and in the end, my actual answer is the starting point plus a sort of averaging between all of these in the case, and it's half K1 plus 2K2 plus 2K3 plus K4. So you see, conceptually it's very similar, it's just you have more intermediate steps. This is fourth order accurate, this is second order accurate. Is this half or 1 over 4? I have to make sure. So
Divided by 6.
yeah, divided by 6. Yeah, it's 2 plus 2 plus 1 plus 1. Yes, yes, divided by 6. All right, so yeah, that would be an average, right? So you're adding 3 different slopes and averaging. All right, perfect. So does this make sense, the concept? Now go back to our channel that we were talking about. And just imagine having to do 4 intermediate steps. So you'd have to do this sort of computation, intermediate computation, several different times. So it's expensive. So should we use RK2 or RK4? RK4, why?
Because we have everything we need.
Yeah, we have everything we need because this is an explicit scheme, right? And RK4 is higher order accuracy. So yeah, it makes sense to use higher order accuracy scheme. But remember we talked about order of accuracy does not mean accuracy. It just means your error will drop faster than this one. So that's one issue. You might not necessarily be more accurate for the time step you're looking at. And the second issue is cost. So this is considerably more expensive than an RK. So from what I used in the class, usually RK2 works sufficiently well. So I stick to RK2. But you can use either. Okay, so this was a very simple example of what happens inside a channel. What about our advection equation? So advection equation was del phi by del t plus 2 del phi by del x equals 0. Okay, so I'm not going to give you the answer, and we are going to work through it one by one. So let's integrate in time using RK2. All right, so step 1. And just to make this sort of conceptually clear in all our heads, this is just a 2D grid, and I know the x, y coordinates of each grid point. I know the phi at each grid point, and I'm just trying to trace this particle forward or backward. Right? That's what advention is. So step 1. What is step 1?
d phi over dt.
All right. So we will say k1 equal del phi by del t, which in this case is okay. Remember, we're working on a tutor, continuous stuff, not useful. So what should we do? Do you get the question? No? Okay. So, fine. K1 is equal to this minus 2 d phi by dt. But what should I do with this? I mean, I have data given at grid points, right? So, discretize. Yeah. So, minus u, let's say j at what? N or n plus 1? Let's look at the equation again, right? So everything is at n. Okay, so at n, and what goes on top?
Phi I plus 1 at n or j plus 1. It's for negative minus phi I
j minus 1.
phi j at n.
Okay, phi j at n or phi j minus 1. Which one? So should I put a minus 1 here?
Was that second order?
That would be center difference.
Center difference.
Second order, yeah. But we saw that that discretization is completely unstable for pure affection. That we saw a few classes ago. So yeah, so we have to use upwinded, right? This is upwinded. All right, and which means uj has to be, for this particular stencil, uj is 1 negative. Yes, you're correct. Okay, make sense? All right, okay. So at time step n, I can compute my k1, which is the right hand side on this whole grid. Right? I'm given phi and I'm given u. Okay. Next step. All right. What is next step? Let's see. So next step is this. So what should I do? The first time you see this, it's a little confusing, but we're just following the procedure exactly as it's laid out. So we can basically do the same thing we did for our 1D channel case. What would the next step be?
Find K2.
Once more?
Finding K2.
K2, yeah, all right. For finding K2, what do we need?
Phi at next time step.
Yeah, exactly. We need phi at n plus half, right? And we said phi at n plus half is phi at n plus a delta t over 2 k1. Okay? all of this is known. I know my initial phi, I know my k1, and I can compute phi n plus I. Confusing or makes sense?
Yes, it's 5n plus 1/2, not 1, right?
Oh, sorry, yes, yes. All right, once we have this phi n plus half, the next thing is to find k2. And what is k2? Okay, you tell me. Which should I write?
d phi by dt at n plus half and t plus delta t by 2.
That's all K2 is.
All right, you were saying this is this plus something.
And let t equal to t plus delta t.
Yeah, n plus half. Yeah. T plus delta t. Okay, so let's go back. So k2 is the derivative at this half step, and the time half step is already implicitly in there, right? So it's just this at half, n plus half, as people was saying. So let's see. So this is minus u j n plus half and phi j n plus half minus phi plus 1 j n plus half. Okay, and in pure advection problems, usually you're given the u, so you don't have to solve for u. You're given that u varies as a vortex, any. For instance, okay, so I think we can switch to the computer now. So yeah, let me just make sure I don't have to tell you anything else. All right, perfect. So let's switch to the computer, and if you remember, if you remember, we had looked at these very simple cases. Right? This was one case. So what I was solving here was just the scalar advection. I was given that the velocity of the field looks a certain way. In this case, it's a rotating field. Okay, so there we would know what u n plus half u basically anything would be. Okay. So yeah, so that's basically how you would solve the advection equation with RK2. We actually forgot the very last step, which is once you have this K2, step 3 is the simplest one, which is you say phi n plus 1 is the original phi plus delta t times K2. And that's your answer, right? So that's it, Runga-Kutta. If you know how to do Runga-Kutta, you know how to do Runga-Kutta. If you know how to do the second order scheme, this one, you know how to do the fourth order scheme, any higher order schemes. They all follow the same pattern. All right, so let's switch to coding, but before that, do you have any questions? No? All right, perfect. So, what do you know about computers? Have you ever considered what happens when we input data in math, right? So that's it. We have MATLAB open here, so let me say A equal 1, 2, 3, 4, 5, 6, 7, 8, 9. So A is a matrix. Can you see it at Go-Karathon? Yeah, all right, perfect. So A is a matrix. What happens in the hardware? Where are these numbers stored? Is it stored on my hard drive? Is it stored somewhere else?
RAM?
It's stored in RAM. And again, the things we will talk about today are good to know because imagine if you're doing experiments, you would need some knowledge of how the equipment works, right? How the lasers work, how the sensors work, how the diagnostics tools work. So it's important to know just a few things about the hardware. All right, so this matrix is stored in the RAM. How is it stored in the RAM? Is there a two-dimensional allocation in the RAM? There's a matrix created in RAM, and then each number is stored there. Have you ever thought about this? I had never thought about this when I was learning. Never thought about it, right? The way computer memory is actually laid out is linear. So there's no two-dimensional or three-dimensional structure. Everything is stored in a line. So what happens is, if I say, give me the 1, 2 index, that would return this one, right? That's the row 1, column 2 index. Okay. What happens if I say this?
It's 4. It goes to the 4th spot.
All right. So one answer is it would return this number 4. All right. Any other answers?
Should be an error.
Error. Why error?
For it's two-dimensional, I think it has to be allocated.
Right. So the answer is there should be an error because A is two-dimensional and I'm trying to access it using a 1D, using a single number. Right? Doesn't make sense. Other answers? Yes.
Other answer is, as you said, is linear, so it might be 4.
Okay. So all right. Now
I'm guessing.
yeah. So that's okay. So it's not a bad guess. The answer should be 4 because it's linear. How did you count? So you counted 1, 2, 3, and 4.
Make a row.
Yeah, you went through the row, but why not? Why didn't you go through the column?
Because it's not stored that way.
So then
It's not stored that way. How do you know?
Trial and error.
Trial and error. All right. So let's see. Trial and error. What does that? Oh, no, that was I just wrote 4. A of 4 is 2.
column.
Yeah. Yeah, it's stored in columns. So it's 1, 2, 3, and this is the 4th element. All right. So if I say A of 6, what will happen?
8.
Yeah, you will get 8. A of 6 is 8. Let me just bring back 8. And that's exactly the reason. In MATLAB, data is arranged in column major order. Okay. Now, every programming language has its own preference. In Fortran, you get column major ordering. In C, C++, you get row major ordering. In Python, you get row major ordering. So if I wrote A of 6 in Python, I would actually get 6, okay, instead of 8. So you just have to know the language that you're using, how does it arrange data. Okay, so let's go back to yeah, so before I wish I had told you. Okay. This is just comparing, so forget about coding for 1 second, going back to what results for Runge-Kutta look like. This is German. So exact answer, classic Runge-Kutta and Euler. So you see Euler, that's the one-step scheme that's very simple, gives you the blue line. It's a bad answer. Oh, no. It gives you the pink line. And if you decrease the time step to half, that gives you the blue line. But the Runge-Kutta, the yellow line, is already close to the analytical answer. That's the red line. Okay.
The second order, right?
What's what?
That's a second order or fourth order? Wrong difference.
I wish they had mentioned that here. I am assuming it's second order, but it can be fourth order. I don't know. But even if it's second order, it's already comparing a first order scheme versus a second order scheme. Right? So it's already it will be better. And yeah, all the Ks that we've been talking about, these are the Ks. So if you follow this one by one, ignore all the lines, and we'll look at what all the lines mean. If this is my starting point, this is my slope at 0, and I take half a step, so that's t plus delta t over 2, and I end up here. And over here, I evaluate the new slope, that's k2. Now, k3 was go back to the origin and take a step with this new slope. So go back here, take a half step with this new slope. This black line is parallel to that red line. All right, that gives me this location. Now, again, evaluate the new slope. Okay, next step, go back to the origin and take a full step with K3. That's the black line you see here. That's taking a full step with K3. All right, we end up here. This is the new slope. All right, so now we have 4 slopes. We take the average and take a full step from the origin. So that's the final black line, the one on top. And you end up at the numerical answer. Okay, so visually that's what happens. Okay, let's go back to fun stuff. Oh no, what happened here? Okay. Okay, fine. So we looked at how memory is laid out, right? And we didn't look at it. We just did some trial and error exercise, and we figured out that it's laid out at 0, right? So the important thing is memory layout in RAM is linear. No matter if you have a 2-dimensional array, 3-dimensional array, 50-dimensional array, it's always laid out consecutively. And if you say give me a 2, 1, it will just compute, okay, 2, 1 corresponds to this linear address, and it will go there and fetch the number. Make sense? In this case, 2, 1 would correspond to 2. 1, 2 would correspond to 4. Yeah. Okay. So let me not belabor the point. So yeah, matrices do not exist on the computer. Everything is stored linearly. And it's either row major order, as you see here. That would be how Python arranges its data, and column major order, that's how MATLAB arranges its data. Okay? All right, and I already mentioned this. No matter how many dimensions your matrix is, so if this is 3-dimensional, the first plane will be stored first. Then you go to the next plane, the one in front of our screen or behind our screen. And then you keep storing in the same way. Okay? So that's how data is arranged. All right, so now, how does this impact our code performance? What you want your code to do is always access as many continuous elements as possible. So when you write a for loop, you want your code to go through A11 to A21 to A31, not the other way around. You do not want your code to go from 11 to 12 to 13. Okay? Because that breaks the continuity in data. And we will see why that becomes important. It can slow down your code significantly. All right, so let's take a look at an example if that's indeed true. Let's go to, all right, yeah, so I will write Have you heard of these things before? Have you ever had anybody talk about these things before? No? Yeah, we will see how the code performance drops by 20 times just by changing a very simple thing. Okay. So let's write some code. Let me write, okay. All right, so let me write a variable code version first. Clear CLC, and let's say we will have 1E4 elements, 10,000 elements. Okay? And A is a random number 1 to n. B is another random number 1 to n. Actually, we said we want to look at two-dimensional arrays, right? So it's n by n, and C is zeros, n by n. And let me not say C is on that. Okay, first let's do this. Okay, simple for loop. I want to add A and B. For index x equal 1 to n. For index y equal 1 to n. Okay. C index n or index y equal A index x index y plus B index x comma index y. Okay, and all right. And if you use MATLAB, there's something called tick tock. So this is just a timer. It will start a timer at tick and do the computation. And when the computation ends, it will say stop the timer. And it will print the result. Okay. So does this code make sense? This is something you would write, right? Can any of you tell me immediately if you see something wrong with this?
You haven't declared C and you're solving for indexes in C.
Yeah, I have not declared C. So, will the code work? Okay, test one. The code works. Why does the code work?
Well, you're defining it in the for loop, but it's inefficient because you didn't declare matrices beforehand.
Yeah, so here, I am defining it inside the for loop, but every loop makes the size of C change. So the hardware has to deallocate what existed in C, create a new copy with enough space, and put everything there. Right? So this is very, very slow. As you can see, this is already killing my computer. So let me stop that, and then we will decrease the number to 1 in 3. Okay, let's see if it goes faster. Okay, so all right, so 0.7 seconds. Fine. Let's see what happens when we do allocate space for C. So now there is space for C. C will not keep changing all the time. 0.03 seconds. Okay. That's a what? It's a 0.7 divided by 0.03. 20 times increase in speed. I did nothing. I just added one line. Now, can you help me optimize more? What did we say? MATLAB is row major or column major? Column major. What is happening inside my loop?
It is accessing it sequentially.
It is accessing it sequentially. Because, why do you say that?
The columns, it's counting the columns first and then the rows, right? Because the y index is inside.
The y index is inside, so let's see what actually happens, right? If we just print these two things inside, we will know who is changing the fastest, right? So let's see. 1, 1, that doesn't tell me anything. Okay, next loop. Index x does not change, index y changes. Next loop. Index x does not change, index y changes.
So you're staying in the row.
Yeah, I am staying on the row and accessing different columns. Good or bad?
Bad for your memory.
Very, very, very bad. Okay? So that's called non-contiguous access. Now, how should I fix it?
Interchange.
Change x and y.
Yeah, change these x and y here. Okay? All right. So do you remember the answer? Okay, we can just rerun. 0.04 it was roughly.
You've got both of them at y.
Once more?
You accidentally retyped y.
Oh, sorry. Index y and index x. Yeah, so now we will stay on a column and run through the rows. So we're accessing adjacent numbers in memory. All right, let's run. 0.016, okay? Let's change it back and see what the original answer was. I will copy this new number. Okay, and then run it with the terrible. Okay, this is the terrible answer.
Twice.
And the good answer was that. So it's almost a 2x increase. Okay. Even with a very small number of points, 183. If I do 184, it should be better. You see, this is the bad index, yeah. Give it a second. Okay, come on. It's not that many. Okay, but you already see, just by arranging your code slightly differently, how much it can affect your performance. Okay, roughly 20 seconds, okay? All right, let's see if we go to do contiguous access. Oh, done. So that divided by 1.46, whatever, 13 times.
Exponentially.
Yeah, if I increase the number of elements more, this will get better and better. And in your computations, you might easily do this 10,000 by 10,000 grid. Okay. And in real 3D computations, imagine this 10,000 by 10,000 by 10,000. That's a huge grid. So even 1,000 by 1,000 by 1,000 would be much faster if you just code it correctly. Okay. All right. So what else can we do to improve the code? You do not have this luxury with every language, but most languages do give you an alternative to writing a for loop. Do we need to write this loop for this operation? No? Yes?
No.
No. Why?
We can write the vectorized version with dot plus all elements. Like we can simply write C equals to A plus B.
Yeah. So with MATLAB, Fortran, and Python, we have this luxury that we don't even need to initialize. We can just say C equal A plus B. Right? And this was the fastest for loop. So let's see. Sometimes it works, sometimes it doesn't. So, oh, no, don't do that.
Control C.
still faster. Okay, so the for loop we wrote was 1.4 seconds, and this is 0.3 seconds, 4 times faster. So now remember, the crappy loop that we wrote was 20 seconds, right? And just with simple changes, you have gained 60 times. Okay? The crappy loop took 20 seconds, and vectorized code takes less than half a second. This becomes very, very important when you're running a long CFD code, because you have to run for several steps, and whether each step takes 1 second versus half a second makes a difference. You have to wait for your result for 2 days versus 4 days, 1 week versus 2 weeks. So think long term, it makes a huge difference. For short things, you usually don't care. You don't need to optimize code a lot. But these are very good habits to adopt. Making sure your for loop indices are correctly ordered. Okay, and use vectorization as much as you can. Okay, what is vectorization? Do any of you know? Yeah, it just means C equals A plus B, but what happens? Why does this work better? Any idea? Why should this work better? It's still doing the same operations, right? It's going through each of the numbers of A are added to each of the numbers of B. Why should this be faster?
Maybe the location of the variables in the memory is nearby. So
the location of the variables in memory is nearby. But we made sure when we wrote our nice for loop that we were doing exactly that. We were accessing elements contiguously. So everything that was next to each other was accessed sequentially. So the reason for
you have a new entity. You have a new entity index and in Y, and this is being stored into the library for the addition, which does not exist when you're doing C equal to A plus B.
All right. So your answer is that we have this index Y and index X that now the hardware does not need to store, right? It does not need to assign index X equal these. Yeah, that's true, but the speed up is 4 times, right? That doesn't make sense. Just with 2 simple variables that are integers, you would get a 4 times slowdown. Okay? So there's something else happening. And that actually goes to the hardware vendors. They have, they keep trying to improve how we do computations. And now, so it used to be that, okay, the way a computation works is, all right, perfect. So we have our CPU, right? The actual transistor that does the A plus B. But before coming to the CPU, data has to be transferred from the hard disk to RAM to something called a cache. Okay? And the speed decreases very, very significantly as we go farther away from the CPU. Okay? So what we want to do is we want to keep our data as close to cache memory as possible. Okay? So registers are much faster than cache memory, much faster than RAM, much faster than hard disk. Okay? Right, so that's one thing that happened in the MATLAB example. This data is loaded into this cache. The matrix is not just present in RAM, so I don't have to go to RAM to fetch my next number. A whole chunk is loaded into cache, which can be at least 10 times faster than going to RAM. And then all of these numbers are taken from the cache instead of asking from the RAM. Okay, make sense? Again, you might not have seen this before, so ask me questions.
Is that because in the loop you're calling a specific location within the matrix? So you have to go back to the RAM?
Yeah, so the cache memory is very limited, okay? It's very limited, so you can store a few numbers in there. Let's say, okay, for an example, you can store up to 2 megabytes, let's say, maybe less, okay? The RAMs are huge, right? They can be gigabytes. So you can only store, let's say 100 numbers in the cache. Anything beyond 100, you would have to go ask the RAM. And that's already 10 times slower. That's why when we swapped the indices, we got such a huge difference. We were accessing numbers stored in cache, not in RAM. Okay, does it make sense? Okay, ask me another question.
Can't we do that with registers?
The registers are actually located on the CPU. What do you mean?
Yeah, instead of like vectorizing for cache memory, can't we do the computation in the registers?
Okay, so the computation A plus B, all of mathematics happens in the registers. Okay, but the register can do A plus B. But there's very limited number of registers on the CPU. Once it's done A plus B for the first 10 elements, it needs the next 10 elements. So it has to ask for them from either the RAM or the cache. Preferably, it should ask from the cache. That's what it does. First, it goes to cache. Oh, it's not here. I have to go to RAM. Then it goes to RAM. So you have to try to maximize the utilization of the cache. Make sense? Registers have to be loaded and unloaded. All right? Yeah? Question for Boca?
Yeah, just a doubt. I mean, so the last point is that the cache memory is very limited. So in that sense, the loop method of addition would be easier if you have a larger size of matrix which cannot be fit in the cache.
You're saying a matrix...
If the matrix size is bigger than the one that can be fit into a cache, then shouldn't the loop method be easier?
If the matrix does not fit into cache, what happens is a part of the matrix is loaded into cache. Okay? So as much of the matrix that can fit in cache is loaded and used. Anything else that's needed has to be loaded again. Okay? Directly onto the CPU or into cache. Make sense? If the matrix is too big to fit into cache, only half of it, let's say.
Isn't that the same thing? Isn't that the same thing done in loop method? I mean, so you can use every column as a loop or every row as a loop. Isn't that the same thing done in the loop method? That you're taking parts of the matrix and adding them.
Yes, yes. So, okay, right now what I'm saying does not apply to why vectorization was faster. Okay? That comes on the next slide. Is that your question? That's the question. Okay, okay. So, yeah, how does vectorization help? I will show you on the next slide. This is just me telling you why looping through your matrix correctly matters. Because of cache. Okay? Let's just look at a comparison of two CPUs that are quite similar. So this is a list of the Intel CPUs. Let's see, how many cores? Okay, let's look at these two. These two should be, perfect. So you see, this is number of cores, okay? Number of cores, 10. This clock speed is slightly higher, and the cache is just 3 megabytes larger, and it's more expensive. Okay, and you see, this is the cache size, 20 megabytes. It's nothing compared to what we are used to now. Okay, we're used to pictures that are, you can easily fit 2 pictures in that and be done with it. So forget about your high performance computation. But these are the most expensive CPUs on the market. These are the most capable CPUs. And that's the cache size. So it's very, very limited. You can fit a very small amount of data. But it's very, very fast. And so that's the story with cache and memory access. And what's been happening over the past few years, you've heard of Moore's law, right? Moore's law is the computations will get 2 times faster every 2 years. Yeah, the CPUs have been getting faster, but memory has not. We have not moved as fast in memory as we have in CPU performance. So that's the limiting factor today. Memory is the main limitation in computation. Okay, we looked at this. All right, so let's go back to the question of why vectorization is important.
So before that, I have a question.
Yeah, go ahead.
So that why do we keep the why the size of cache memory is kept small?
It's not intentionally kept small. It's just physical limitations and technological limitations. I could not tell you the exact hardware reasons, but the cache memory is located very close to the chip. Okay, and there's limited, again, resources you can allocate to it. So it's always a trade-off between how much you can put in versus how much resources should go to other places. It's been slowly increasing. When I started my doctorate, it was a nice cache size was 6 megabytes. Now it's 20 megabytes. So yeah, it's increasing, but very slowly. Okay. Another question? Okay. These are low-level details. It's good to know, but the important thing is you should ensure your loops are ordered correctly and always use vectorization when possible. All right, so vectorization. Nowadays, what happens in hardware is they have something called Symbian processors. Let me see, did I mention Symbian here? Symbian processors. Single instruction, multiple data. So what happens in these is instead of doing A times B, 1 by 1, you load 4 elements from A and 4 elements from B simultaneously and do this operation in 1 clock cycle. You know what a clock cycle is? All these CPUs you've heard of, it's 1 gigahertz or 2 gigahertz, nowadays even 4 gigahertz. That's how many clock cycles in 1 second. Okay? So you can do 1 billion individual computations in 1 second. Seems like a lot, but if you're doing this in 3D, it would take 1 second to go 1 step for 1 A plus B. Okay? Just not a lot. So that's when these vector processors come in, these Symbian processors. They load multiple elements from these arrays onto the registers and do this operation in a single cycle. Okay? And again, there are limitations. I think the newest Intel CPUs can handle 4 floating point numbers at 8 floating point numbers simultaneously. So if I have 5, this is the older version where it could handle 4 numbers simultaneously. So if I had 5 numbers, 4 of them would get computed in a single cycle, and the next cycle would compute the remaining numbers. All of this makes sense? Okay, ask me more questions.
But then it would be like hardware specific on which systems I can use.
Yeah, exactly. It is hardware specific. So when we write very low level code in Fortran or C++, we have to be very careful to tell the compiler that, yeah, this Intel CPU has 4 simultaneous a vector size of 4. Okay? Or the newest one has vector size of 8. Okay? So yeah, you have to tell the compiler that. And if you do it incorrectly, then it can actually slow down your code. Okay? Because the compiler will try to do this, but will be unable to, so it's not optimized anymore. These are very low-level things that we have to worry about in high-performance computing. More questions? Nothing else? So we've talked about pre-allocation, we've talked about vectorization. So now you should have an idea of how to structure your code when you write. I've shown you MATLAB examples because that's what I'm familiar with. So the same things apply in Python. Okay? If you use Python, just ask Google how to do these things. I actually want to stop there for today, and we will continue with interpolation and other things next class. Do you have questions about the project? It is due on February 7th. Please start early. It's not a very difficult project, but it might take some time to get it working correctly. Okay, if there's no more questions, we'll stop and I'll see you Thursday.
Thank you.
Sure. And can you come after lunch?
No.
No, go eat. Go keep going.
Is there any book in which these things are written? Like
For
how
computing?
to, yeah, take into account the hardware so that code runs more efficient.
I forgot to show you the profiler. Yeah, I will show next class. I don't know. I had to learn from experience and from talking to computer scientists. So yeah, I'm not sure. I can look for it. Yeah, I will look for it and I will tell you if I find something.
I think there is one, because I'm pretty sure we had to read it.
Yeah.
It's like the very first chapter, so nobody paid attention to it. But I can check it and bring the book tomorrow, if you want.
Do you know
Yeah.
what it's called?
I cannot remember.
Okay.
No. But it's literally sitting on my desk, because I've had to use it like 20 times in the last semester. But yeah, I'll bring it in tomorrow. I'll check it first. But I remember the very first chapter talks about RAM and stuff like that. But I mean, it's been like 5 years since I read the first chapter. So I'll check it though and bring it to you tomorrow. Thank you. Are these actually the code examples you had listed? Are they examples that you're going to put on Canvas?
Code examples?
Yeah.
For this?
The last slide you wrote code examples.
Oh no,
And
that's
then-
just what I was writing.
Oh, okay. All right.
So-
I typed it all out while we were doing it. So.
Okay.
Yeah, it was just these examples. So this one's the vectorized.
Mm-hmm.
Okay.
Yeah.
All right. Perfect. Thank you.
Sure.